The algebraic method. Number 3. The algebraic method involves the equations that describe the motion of both car 1 and car 2. For example, when we did the battery of buggies lab and plotted our d versus t graph, we actually came up with the equation. We saw it in the graphical method, and that's this here. D car 1, which is the displacement of car 1, is equal to the velocity of car 1 times t. This velocity, of course, is the slope on the d versus t graph. So this is where we got it in our battery of buggies experiment. So there's a relationship between the graphical and, of course, algebraic. There's just two different ways to describe the motion of these cars. The car 2 is equal to v2g plus t. So here's the slope, again, of the d versus t graph. The difference now is that it has a head start, and that head start, which we call dh, h representing head start, is the y-intercept. So this is the y-intercept on a graph, but here it is algebraically. And so because we have algebraic expressions, we can solve for them quite easily using the techniques of SADMAP. So wrote it down over here. Our strategy is to set displacement of car 1 equals displacement of car 2, and then solve for t. When they meet, they're going to be at the same displacement relative to the origin, which is at the start of car 1. So we've got v1g times t here, because d car 1 is equal to d car 2, and it's equal to v2g times t plus dh. So really what I'm doing is I'm taking this expression here, bringing it down here, and this expression over here for d car 2, and bringing it down here. And now I'm solving for t. All right. v1g times t minus v2g times t equals dh. What I've done is use SADMAP. I've noticed I've got like terms. I've got to combine like terms on the same side of the equation. So this one was a little bit messier here, right, with the dh. So ironically, I'm isolating it, but only temporarily. So I am subtracting out this v2g and putting it on this side. So we have this expression here. Now both these terms have a t in it, so I'm going to factor out a t, leaving inside the parentheses v1g minus v2g, and that equals dh. The last step to solve for t is to divide what the content of the parentheses has. So t equals dh divided by v1g minus v2g. All right, so this is our final algebraic expression. Very important in the process of using algebra when we get into more sophisticated equations and relationships. Then this method becomes even more important. You'll see the value of that probably in a few weeks' time. I know that you're skeptical now. You want to plug the numbers in right away. No, not happening. But since we have this for t over here, now it's time to evaluate the expression. We have the values from before. v1g is 5 meters per second. v2g is 2 meters per second. And dh is 5 meters. That's the head start. So now I've plugged in the values according to this equation over here. And I get 5 meters divided by parentheses 5 meters per second minus 2 meters per second. So it's 5 over 3. And I tend to, in physics, write things in decimals. Most of our data comes in decimal form. Even though 5/3 is a nice fraction, I'm going to just make it a decimal here, because that's the way our data is going to appear. All right, and so that's the preferred way to go. Even in some cases where the numbers are large enough, we use scientific scientific notation. Okay. Well, great, we got the time, 1.66 seconds. Well, that's only part of the answer, because we also want the displacement at which they meet. All right, what I do is I take this 1.66 seconds, now I have a value for t that tells me when they meet. I'm going to plug it in. So for d car 1, it's v1g times t, which is 5 meters per second times this t at which they meet, 1.66 meters per second. And over here, that comes out to 8.3 seconds, which really matches our graphical method that we saw with Logger Pro. dCAR2 is 2 meters per second. Here it's v2g times t, the 1.66 seconds at which they meet, plus the 5 meter head start, 8.32 seconds if you use your calculator. Get that out. What's the difference here? How come this is 8.3 and that's 8.32? Well, our data is always going to have some rounding errors, and that's kind of how it works. Sometimes the numbers could work out perfectly with proportions using fractions, but normally when we use data, we're going to find that there might be some slight rounding issues, but essentially these numbers are the same. In physics, we call that the same velocity. That's a good result to get. All right, so we've got one more method to go, and that is, can we guess? It's the relative velocity, the eponymous method.